In this video, we're going to be working out a couple heat calculations in order for you to understand thermal energy and phase change energy and all these constants that you see on the screen. So let's start with our question to the left here. We have a 50-gram piece of ice at negative 10 degrees Celsius that melts completely. Determine the total energy change for this process. So typically when you take a look at these phase change graphs, you have something that looks like this, where you have heat being added and then you have the temperature along the x-axis. What you want to do is just do a quick sketch of the process just so you can visualize all the different processes that are happening throughout the problem. So for this one, we have ice at negative 10 degrees, so I'll just go ahead and make my negative 10 right over here. And it's going to melt completely. So it's definitely going to warm up. It's going to hit 0 degrees and then it's going to melt completely. Anytime there's a phase change, the graph is going to plateau. So we basically have two portions of our graph. So we're going to have to do two calculations. Now, anytime a substance is absorbing heat and changing temperature, then we're going to want to do a thermal energy calculation for that portion of the graph. And then anytime there's a phase change, then we're going to want to do a phase change calculation. All right, so let's talk about the differences and how you're going to approach each of those. Let's go ahead and do the first portion of it and do our thermal energy calculation first. So ETH, and we have that formula right over here, is mc delta T. So m is the mass, m is the mass of the substance, C is the specific heat value, which we'll talk about in a moment, and then delta T is the change in temperature, which is always the final temperature minus the initial. Now, if we're taking a look at just this portion of the graph right over here, we can go ahead and start plugging in our values. We have a mass of 50 grams, which was given in the problem. And then we have three different C values. The subscripts are sort of small, but we have 2.06 for ice, 4.18 for liquid water, and then we have 2.02 for steam. So in this case, because it's below 0, we know that it's in the solid phase of being ice. So you definitely want to know that 0 is the freezing or melting point of water, and 100 degrees is the boiling or condensation point for water as well. Now we got 50 grams for the mass, and then the C value we're going to grab is going to be the 2.06. So 2.06, and the unit is joules over grams degrees Celsius. So it's how many joules of heat energy are required to raise 1 gram of that substance by a degree Celsius. And then for our delta T, it is heating up. Its final temperature is right over here, and its initial is right in the beginning. So our final is going to be 0. And we are going to subtract negative 10 degrees from that. Okay, so 0 minus negative 10 is basically just going to be positive 10. So we're going to take 50 times 2.06 times positive 10. And then we have an ETH value of 1,030 joules. All right, so that's how much energy is absorbed by the substance in order for its temperature to increase from negative 10 to 0 degrees in its solid form. Secondly, we're going to go ahead and take a look at our plateau. Anytime there's a plateau, we're talking about some kind of phase change. Now, we of course wouldn't use the formula mc delta T because there's not even a delta T. If we put in a delta T, it would just be 0. That's where we use this second formula over here, which is just m delta H. Now, just like our C values, we have three different delta H values. We have delta H of fusion, 334. We have delta H of vaporization, 2,260, and we have delta H of sublimation, 2,590. Okay, now this one is in its phase that it's melting, which is going to be our first one. It's going to be 334 joules of energy per gram to get it to go through that phase change. Okay, and it's mass times delta H. And I forgot to put the mass in first. I'll just go ahead and put it in second because we're multiplying them anyway. So we could do 50 times 334 or 334 times 50. We're going to get the same product either way. So our delta H of fusion, our first one, our 334, that's going to be if it's melting. If it was freezing, it would be negative 334. We have a 2260. That would be if something is vaporizing, and if it was condensing, it would be negative 2,260 joules per gram. The last one, sublimation, going from a solid all the way to a gas or vice versa, is going to be the rarest one. We might occasionally use that one, just not in this particular video. All right, back to our calculation. We have our EPH value, and that is the amount of heat energy absorbed to change phases, which is 16,700 joules. Okay, that one is quite a bit more than our ETH. Now, all of that energy that's being absorbed doesn't go into heating up the substance, just rearranging the molecules so it can go from a solid to a liquid. Now, if we want to get the total energy, because we want the total energy of the process, we just have to simply add these two. So we have 1,030 joules plus 16,700, and then we have our total of 17,730 joules. All right, so main takeaways for our first problem, you definitely want to graph it out. Anytime where you have some kind of slope, you're going to use your ETH formula to calculate the amount of heat being either absorbed or released. And then for any kind of plateau or phase change in your graph, you're going to use the other formula, the M times delta H, to talk about the amount of energy absorbed or released in order to change phases. All right, that concludes the first question. Let's go ahead and get to the second one. All right, so for our question in blue, we have 115 degrees Celsius steam that's cooled until it becomes 40 degree liquid water. Again, let's go ahead and make a little graph here. We have how much heat is added versus the change in temperature. So we're going to start all the way up here. We'll call that our 115 degrees, and is cool it until it becomes 40 degrees. Okay, you want to be cautious here because if we're crossing one of the significant temperature values of water, like 100 or 0 degrees, it will definitely make a phase change. So it's going to go from 115 to 100. And once it reaches that point, it's going to condense, so it's going to plateau. And then after it finishes absorbing that energy or releasing that energy to condense into water, then it's going to drop back down and cool down to that 40 degrees. Okay, so if it crosses that 0 or 100 degree threshold by going up or down in temperature, you want to make sure you have it plateau for a bit and then solve for an EPH during that plateaued region. All right, so it looks like we have three calculations here because we have one point where it's cooling. That is an ETH calculation. Same over here, ETH calculation. Okay, I'm already anticipating those should naturally come out negative, releasing heat to make the temperature drop. And then in the center here, we have one EPH, a phase change calculation. All right, let's go ahead and do both of the ETH ones together. So we have the ETH in the beginning. We have 100 grams of this steam. Okay, now steam is in the gas phase. We're going to want to grab this C value over here. Okay, that's a specific heat for steam, 2.02 joules over grams degrees Celsius. And then the ending temperature is right over here, and the starting was up here. Okay, so it's always final minus initial. Okay, and if you see 100 minus 115 is going to give us negative 15, which is good because we do want a negative value for our ETH, showing that heat is being released into the system or the surroundings. So now that the heat is being released into the surroundings, we get a negative value after we multiply these three, negative 3,030 joules. Let's go ahead and do our second ETH calculation, where this one, the initial temperature is right here and the final temperature is over here. It's still 100 grams. This time it has changed into its liquid form, so we're going to grab this number, 4.18. And then our final temperature ends at 40. And then after it became a liquid, it started at 100. Okay, again, 40 minus 100 is going to give us negative 60 because the temperature dropped. And then we find the product of those three, and our ETH comes out to 25,080 joules. Okay, that's significantly greater because it had a much bigger drop in temperature as opposed to the first one. All right, now our EPH calculation. Okay, we have a mass of 100 grams still, and then we want to find the proper delta H. This time we are using the delta H of vaporization, also known as the enthalpy of vaporization, and this one is going to be 2260 joules per gram, but because the temperature is dropping and it is condensing, it's going to be a negative change because, again, it's going to be releasing energy into the surroundings as it is cooling and changing phases in the downward direction on our graph. So our EPH value for this one is going to be negative 226,000 joules. All right, this one's a big one because our phase change takes a lot of energy to be rearranged back into a liquid. All right, now for our total, all we have to do is simply add our three numbers, this one, and this one, and then we have our final answer. All right, my answer got a little squished there, but negative 254,110 joules as the total energy required to complete this process, the amount of energy lost by the system into the surroundings to complete 2 thermal energy changes and 1 phase change. So to sum things up, definitely graph first. Identify where you have temperature changes and phase changes. Anytime for water, at least when it's crossing the 0 or 100 degree threshold in either direction, make sure you plateau it so that you can do an EPH calculation. If you're doing an ETH calculation, make sure you grab the right C value for which particular phase it's in, whether it's solid, liquid, or a gas, and then make sure you take your final minus initial temperature for your delta T. When doing the phase change, that one's a little bit more simple. You want to grab your mass and then the proper delta H of fusion for melting or freezing, delta H of vaporization for vaporization or condensation, and then the delta H of sublimation if it's going from a solid all the way to a gas or a gas all the way to a solid, which is known as deposition. And also make sure you include the negative with the delta H if it is something that is cooling down and losing its heat energy. So I hope that was helpful to you. Thank you for watching and listening.